ahead and start the recording. Okay. On behalf of SPTC, I'd like to welcome everyone to this webinar. My name is Michael Molina with the SPTC and the Oklahoma Transportation Library. We have an exciting presentation today, but first I'd like to remind everyone to please hold your questions until after the presentation. Please keep yourself muted until the end, and once our presenter is finished, you can unmute yourself and ask your questions. As a reminder, professional development hours are going to be provided, and they'll be based on the amount of time that you're logged in. So make sure and stay for the whole session if you want to receive the full hour of your professional development. Our speaker today is Dr. Shreya Vimuganti. She's assistant professor at the School of Civil Engineering and Environmental Science at the University of Oklahoma. She received her PhD from the University of New Mexico, and her research focus has been developing innovative technologies with cementitious materials and fiber-reinforced polymer composites. Today, she's going to be talking about infrastructure rehabilitation with innovative fiber-reinforced polymer composites. So without further ado, I'd like to turn it over to Dr. Vimuganti.
This talk today. I appreciate your time. Just want to share my screen here and get started. So the topic for today that I'd like to present is infrastructure rehabilitation with innovative fiber reinforced polymer composites. This is a very important topic because as we look into current state of infrastructure, we've reached heights that past generations haven't, and we're in a great and exciting phase of infrastructure in America's development. However, the challenges that America's infrastructure is facing are also very new, and with the changing climatic conditions and the new vulnerabilities to risk, there is more than ever need to protect our infrastructure and to make sure we have a long-lasting and durable infrastructure. ASE Report Card 2021, we have a grade of C- for America's infrastructure, which really means that there is more need than ever for new and innovative techniques, materials, and technologies, and also delivery methods. And we want to be able to implement these new techniques to improve our infrastructure and to get this grade improved. We need materials that can provide durability and resilience. For example, if you take the Surfside Miami condominium collapse in 2021, we're looking at a 40-year-old reinforced concrete building, long-term degradation of the concrete supports due to water penetration, and resulting in corrosion of the reinforcing steel. This is one of the major red flags that reminds us that our America's infrastructure is facing new challenges, and these kinds of innovative materials that I will be discussing in this presentation have much more need than ever. So in addition to looking for innovative materials and technologies, we also want to look for cost-effective ways to address this aging and deteriorating inventory. And in the same aspect, we need minimal impact and non-destructive methods for evaluation, which I'll be discussing in this presentation as well. We want these different kinds of new additions to facilitate efficient engineering discussions and decisions. There are a lot of materials that we've seen in the age of our civil engineering and transportation development. I'm going to particularly be talking about composites and how they've affected our infrastructure and the development, and how additional improvements and enhancements can be brought into these materials, particularly, which in turn affect the way infrastructure can develop and become more durable. Ashby charts, looking here in slide 3, we see that GFRP, CFRP, which are basically glass fiber reinforced polymers, and carbon fiber reinforced polymers, which are some of the basic composites that we will be looking at in this presentation today. But if you see the Ashby charts, we can observe that they are in that more good strength to weight ratio as well as good stiffness to weight ratio materials when compared to wood, just polymers, and other kinds of materials. So in these innovative materials categories, we're not looking just for materials which can improve strength and improve other mechanical properties, but we also want to look at long-term durability. We want to look at lightweight to promote other engineering decisions, high impact strengths. In addition, rapid installation is also a very important parameter. Having the capability for a low maintenance over the lifetime of the structure, a high strength to weight ratio, and corrosion resistance, which is highly regarded with the growing steel corrosion challenges that our infrastructure is facing. So durability, which is our ability of this physical system to remain functional without requiring this excessive maintenance and repair in its lifetime when faced with the challenges of normal operation and over the entire design lifetime of the structure. So if we look at these man-made composites, we have the natural composites like wood. We have composites that are man-made, especially looking at fiber reinforced polymer composites. They are two or more materials with distinctly different physical or chemical properties, and they are combined to obtain more desirable combination of properties. Now, these two materials are primarily a thermosetting resin and the fibers that we see available in different forms. In late 1800s, man-made synthetic resins, which could be converted from liquid to solid through that hardening process called polymerization. In late 1930s, Owens Corning Glass Company developed a process for drawing glass strands into these thin strands or fibers and began weaving them into these rovings or textile fabrics that you see here. So these are the different fiberglass forms that we see, whether the drawings or the rovings or the fabric or textile kind of form, primarily used with thermosetting resins to form that hardened final product. So composites were primarily used in the initial days and are continued to be used in aircraft and aerospace industries. If we consider the Airbus A350, 53% of the system is made up of fiber reinforced composites. Now, the primary reason for that is not only its high strength, but that lightweight that enables a better design and efficient design functionality. If we see the Boeing 787, we have 50% fiber reinforced composites used in that particular system. And if we see civil engineering industries, more and more acceptance for these fiber reinforced polymer composites can be seen. We have the wind industry accepting them since many decades for blade manufacturing in terms of wet layup. For different kinds of pressure tanks, water tanks, to resist that high strengths and intensities and impact. Different kinds of reinforcement with rebars and sections, but also strengthening applications with externally bonded systems for existing corroded concrete sections, reinforced concrete sections, or to improve the serviceability and to provide additional capacity. Some of the different processes that can help us understand better what kind of innovations can be brought. First and foremost, this open kind of molding process for these FRP systems, which is a hand layup, where the fabric is basically just impregnated, rolling the resin on top of it and enabling that impregnation of the resin into different layers of the FRP, and following the hardening and curing process, offering that high strength composite sheet that we can see using the hand layup. Hand layup can also be accommodated with vacuum infusion, where you have any additional resin that's eliminated from the process, and it ensures higher strength and higher consistency in the process of manufacturing. The spray up technique ensures that there is as much as needed resin used for impregnating the fiber sheets and fiber textiles and fabrics for the sheet formations, and pultrusion primarily used for bars and sections, with different kinds of rovings that are used by impregnating into the resin and following the curing process and the heating process with a dye. Looking at applications directly, we have many structural systems that have been used and transportation systems that have been used, that have been developed using FRP. Just considering one example here with the 30 years of the Aberfeldy footbridge, which is the world's first major advanced composite footbridge. And there was an urgent timeline and a need for an affordable solution to strengthen and to protect this footbridge. And the parapets were developed using the pultruded GFRP e-glass fiber and polyester resin combinations. The cables were with Kevlar 49 fibers with low density polyethylene. So combinations of different kinds of fibers and thermosetting resins, a deck with the pultruded GFRP sections, and so on and so forth. If we look at the Kentucky footbridge, this is a composite deck with galvanized steel towers and suspension cables that support this pultruded fiberglass. The original wooden footbridge that was built in 1930s had fallen into disrepair, and 100 years of maintenance-free bridge is expected with this rehabilitation that was performed with FRP. Coming to the very famous pedestrian bridge in Virginia, the Wolf Trap National Park of Bridge. In 2012, this national park had that existing trap road bridge over the Dulles Access and Toll Road. This was for vehicles only and did not provide a safe access for pedestrians. So the Federal Highway Administration required an accelerated way of construction to reduce lane closures that would hamper access to the busy airport. So the deck panels that you see here were prefabricated, including the wear surface, the curbs and expansion joints, and this reduced any on-site construction time. More importantly, again, the FRP bridge deck is 80% lighter than a concrete deck, and it was made to lift it easier, faster, and move and just place it with a crane. So coming to some state-of-the-art research implementations and research ideas, and more direction to innovation in these kinds of materials, I'd like to start off with nanomodified resins for FRP enhancement and the work that has been prevailing and I was involved with, and what the future looks like in terms of these nanomodifications. Now, the resins that I talked about, the thermosetting resins, which are used with the fibers, which form primarily that composite system, they are used with fibers, and during the curing process, there is cross-linking that happens, which forms an irreversible bond with these fibers. So the bond between the resin and the fiber is a highly crucial element in the strength and resulting mechanical properties and the properties that has inherently the fiber reinforced polymer composites offer. So different resin types and different fiber types are usually combined, but looking particularly at nanomodifications, carbon nanotubes particularly stand out when we talk about nanomodified resins. In carbon nanotubes, there are both pristine and functionalized with different kinds of functional groups. I have worked with carboxyl functional groups particularly, and looking at the results of different resin modifications with these carbon nanotubes, the functional group of carboxyl improves bond between glass fibers and epoxy. And this potential chemical reactions improve the adhesion strength, bond strength, cohesive strength, shear strength of the fiber matrix interface. So if we see these epoxy nanocomposites, the fiber that has silane sizing agent reacts with the carbon nanotubes in the resin, forming a much better and much improved chemical reaction and resulting bond. So looking at the applications of this, one particular project that I was involved with is how we can improve shear strength of FRP particularly. We have FRP that is being used in so many other applications in civil infrastructure. However, its widespread is still hindered because they are restricted in usage as dowels for bridge decks and slabs on grade, and also as reinforcement in shear critical regions in reinforced concrete structures. So in applications with higher shear demand and the design with the current FRP, if we consider in these applications, it will lead to inefficient design and also increase the cost thereby. So in order for FRP to become more accessible and having more improved shear strength, we have seen that pultruded sections with nanomodified vinyl ester resin have definitely impacted the shear strength and resulted in improvements. So if we see generally the resin modification process resulting in these improvements, it's a fairly simple process with the carbon nanotubes that are measured as at least about 0.5 to 1.5% or 2% of the weight of the resin. So very, very small quantities of these carbon nanotubes has also shown huge improvements in shear strength. The modification process is fairly simple in involving this mechanical stirring process and an ultrasonication bath in order to split or break the van der Waals forces between these different carbon nanotubes. This nanomodified resins can be analyzed for their behavior or how the dispersion process is effective or not using scanning electron microscopy. In this particular fracture surface, we see that there is a lot of good dispersion of carbon nanotubes in the resin. Coming to viscosity measurements, because pultrusion is a study of, pultrusion is a manufacturing technique that involves impregnation of fibers and a pulling process with a certain speed. Viscosity measurements have to be checked in order to ensure that this nanomodification of the resin is not affecting the viscosity and rheology of these resins. So as we can see, there is very minimal differences between the nanomodified resins and a control resin of the vinyl ester neat. So this fact that the selected amounts of MWCNTs, which are multi-walled carbon nanotubes, it does not affect viscosity or the fiber wet out process. That means itself that there is no need to change the existing pultrusion process that we have, that the industry has widely accepted. And we only need to have one-time investments into the dispersion of nanomaterials in the vinyl ester resins or any other resins for the pultrusion process. It has also been very effective to understand that the carbon nanotube modifications in the vinyl ester resin has not affected the curing process of these resins. So the curing, however, of both the cured vinyl ester neat without any nanomodification and the cured vinyl ester with a slight amount of nanomodification with the carbon nanotubes still have shown to have 95% of curing capabilities. So looking under tensile loads, it's a very, very good improvement of 20%. The main idea is to see that brittle explosive failure in a neat FRP, whereas not so brittle and not so explosive failure in a carbon nanotube modified FRP. With the main focus, which was the shear strength, huge improvements were seen due to this nanomodification. About 110% improvement in the shear strength was seen with the resin modified with carbon nanotubes versus resin not modified with carbon nanotubes. It has seen a huge improvement even with market available GFRP. And it was a very, very crucial thing to observe that these nanomodifications can bring in a lot of enhancements. So confirmations of these studies included Fourier transformation infrared analysis to understand what kind of chemical changes were seen in this kind of nanomodification, how the nanotubes are reacting with the resin, but also how these nanotubes are reacting with the agents on the FRP itself, the silane sizing agents, and how they form the bonds with the carbon nanotubes, resulting in better enhanced bonds. So we see definitely a lot of future in the nanomodified pultrusion in terms of producing sections, in terms of also enhancing this nanomodification process. There are different techniques in addition to the ultrasonication and mechanical stirring, including 3-roll mill or calendaring process, ball milling. These techniques especially have that shear capabilities where there are, for example, 3 different rollers running at different speeds, and these rollers act against each other and rotate against each other at varying speeds, creating that shearing action and resulting in a more dispersed and evenly homogenized mixture towards the end. Additional capabilities that we can be looking at in the possible future with the nanomodified resins is the capability of advanced imaging and mapping. We do need some very good non-destructive evaluation techniques to observe any kind of defects or challenges that we could possibly face in the future. And what happens with these carbon nanotubes is they improve the ecogenicity of any solutions that can be incorporated with them. For example, if we see this particular picture where we are using water, graphene oxide, pristine, and modifier functional group MWCNTs and with ammonia, we see that the ultrasound signal is very high in these nanomodified solutions with carbon nanotubes. This can help us improve the imaging process that there is right now and also add to the capabilities that we have for non-destructive evaluations. If we look at externally bonded rehabilitation, a lot of future in this direction as well. We see ACI 440 that governs the flexural strengthening of reinforced concrete beams and the shear strengthening of reinforced concrete beams. The flexural strengthening with near surface mounted FRP, where a socket groove is made on the tension face of the beam. The groove is first half filled with epoxy and additional FRP reinforcement is placed in this groove, and then the groove is completely filled with the epoxy and left to cure. Coming to the URAP FRP shear strengthening aspect, we see an FRP laminate that is bonded to the tension face of the beam using epoxy polymer to allow the FRP laminate to act as additional reinforcement, and it contributes to the overall flexural capacity of the beam. Most times what happens is these two techniques are also combined in the field, but currently there are not enough guidelines established on how the failure happens, what are the possible failure modes of RC beams, strengthened with not only just NSM FRP, but also this URAP shear strengthening. There's been a very, very crucial work that has been conducted, and future research is surely warranted to identify the significance of both URAP and the near surface mounted FRP, not only on the capacities, but also fatigue performance, and understand how the strengthening can affect that particular aspect. For culvert rehabilitation, it's been gaining a lot of importance, especially because of the replacements of culverts that's necessary. Chemical ingress and toxicity in the water has increased in the past decade, and culverts have been seeing more and more degradation and replacement costs in this particular challenge. So the retrofit and rehabilitation of existing corroded culverts is more important than ever, but more in an aspect of reducing the costs related to culvert rehabilitation. In-place retrofit is receiving much more importance. So corroded metal culverts are showing, of course, loss of cross-section, and the failure of these corroded metal culverts is really just inevitable, especially with the corrosion, and if you consider a long-term aspect. So the cost associated with road closures, maintenance and replacements is substantially high, and design life really just drops below 30 years. So the aspect of looking into rehabilitation of these culverts with glass fiber reinforced polymers has been conducted, and a lot of more work is definitely needed in this particular aspect, especially because now we know that we have carbon nanotube resins that can improve imaging and mapping, in addition to improved mechanical properties. So glass fiber reinforced liners, these polymer liners are suggested for structural retrofit. It's a slide-in GFRP pipe into these corrugated metal pipes. So in-place retrofit is really just possible with simple techniques that can not only strengthen this particular this particular steel corroded sections, but also improve lifetime and improve the overall cost of maintenance and replacements. So we do see that both computational and experimental analysis have shown that corroded and non-corroded are really performing on par with each other with this retrofit using GFRP slip liners. We have different models that can be used to study what kind of bond capabilities with the grout and with the existing corroded steel sections can be offered with the FRP. Nearly 100 years of lifetime and assumed service life is expected with decreased service costs and overall maintenance. Durability and extreme weather conditions are, of course, the need of the hour. The challenges is to understand performance of FRP composites in long-term behavior, creep and fatigue, of course, but also harsh environments like extreme temperatures, chemical attacks, and freeze-thaw cycles. So the durability of FRP composites in other applications like aerospace and naval applications have had past information available. But in civil engineering, this data is still very, very limited, and there is a lot of future and potential in this direction to understand what the durability of FRP is. So this lack of data on the durability is definitely right now a major obstacle to their acceptance on a broader scale in civil engineering. And as the methods of FRP fabrication and environments to which civil engineering structures are exposed, they are quite different from the other engineering applications that we've looked at, like aerospace applications and wind energy applications. So these environments need to be studied in more detail, and these become pressing concerns because wherever there is corrosion, either due to chemical ingress or the water penetrations, there are applications for FRP in those regions, and understanding how their behavior is with these environments that are existing is definitely important. So if we consider one particular extreme condition of UV, UV causes a relatively high degradation of FRP. For example, if you look at the non-exposed UV, non-UV exposed FRP versus UV exposed FRP, you already see a color change. But we've seen that nano-modified resins can also add lot of enhancements and improvements in this UV-related challenges. So if you have the tensile strength unexposed already, if you see carbon nanotubes are improving their tensile strength, but if they are exposed to UV, these strengths are even more definitely improved and enhanced. For example, 1% of the resin, weight percent of the resin carbon nanotubes in a UV exposed sample already shows a 16% improvement in the strength of the material. Of course, the brooming brittle failure can be seen transitioning into a more non-brooming and less explosive failure. In addition to those mechanical property improvements and enhancements, you can also see from scanning electron microscopy that by dispersing these NWCNTs to polymer matrix, you can clearly see significant bond dissociation within the polymer matrix without the MWCNTs. So with a 0% MWCNTs of unexposed versus UV exposed can be slowly transitioning into bond dissociation and polymer matrix degradation. So samples with MWCNT showed a lower bond dissociation, and this is really just attributed with the C double bond with the oxygen. So from these different kinds of behaviors, we can see that by dispersing carbon nanotubes to polymer matrix, new kinds of polymer nanocomposites can be developed, and their inherent properties and stability to UV radiation can be improved. Considering freeze-thaw conditions, this is one of the primary types of environmental stress that seriously threatens the service life of concrete structures in cold regions. And when FRP composites are used in civil engineering structures, the properties of FRP composites and the bond capacity between FRP and concrete may be degraded with increasing freeze-thaw cycles. So it's very, very important to understand these behaviors in the extreme conditions of a freeze-thaw. So currently, our team at OU is working on investigating the freeze-thaw behavior of FRP with traditional conventional FRP and also nano-modified resins incorporated for FRP, and how this behavior affects that durability. This work has been seen in the past literature where FRP composites are in a state of stress in real strengthening applications. And with respect to the service loads during the freeze-thaw cycles, cyclic thermal stresses on the fiber matrix interface are likely to be magnified, and there are more microcracks that can be developed due to these freeze-thaw cycles. So the consideration of combined effects of harsh environments as well as service loads is very, very important to understand, and the behavior of FRP in this application is really need of the hour. In addition to to the service load behavior as well as the different kinds of effect that the freeze thaw has on FRP, it's also very important to understand how the bond changes between the resin and the glass fiber, how this freeze thaw can affect the bond, and because bond is such an important parameter in this composite behavior, what kind of changes happens with freeze thaw cycles, and is there any thermal incompatibility of these constituent materials, the vinyl ester monomers, the styrene component, the silane sizing agent of the glass fiber. Is there any incompatibilities due to the freeze thaw and the moisture environment, and what kind of damage that the FRP composites experience, and how consequently this influences their tensile properties. Coming to very, very advanced and very current futuristic aspect of FRP that was my PhD dissertation is how can we bring ductility into FRP using just one single type of FRP or one single type of fibers. If we see the FRP behavior, typically we have steel, a very nice ductile material with failure strains higher than 5%. However, typical GFRP and CFRP are very, very linear elastic to failure, and their failure strains are less than 2.5%. They are high strength, high stiffness materials, but do not exhibit or do not demonstrate a ductility or a yield plateau like steel does. So this linear elastic behavior has been attempted to change and transform into pseudo-ductile behaviors, but very low strains were still observed and the strength decrease was very, very significant. Ductile behaviors were observed, but though they looked at larger strains at failure, that failure strength was very, very low, which really produced negligible improvements. The proposed FRP system that I have looked at and also we are looking at currently are a more ductile and having a high yield plateau and high failure strengths, but also preserving that strength and stiffness and coming close to what steel can offer. The way that this particular implementation was adopted is using this anisotropic FRP. Now, FRP has different properties that can be observed in different fiber directions. So starting from 0, which offers that high strength, high stiffness material property, we transition slowly into different kinds of angles, which in turn reduce the capacity and stiffness, but improve the strain of and non-linearity of these FRP. So if we see this the transformation from a high strength to a low strength, we see that non-linearity being increased with every fiber orientation. And this particular aspect is used in this new innovative FRP composite systems with 3D printing. So what 3D printing offers is very, very interesting because advanced 3D printing technologies currently have the capability of not just printing thermoplastic spools, but also printing with fiber spools. This can be simultaneous, and this can also be one when one is running, one does not run. And this is basically resulting in a selective reinforcement capability. So this advanced 3D printing technology is beneficial in producing FRP composites with engineered stacking sequence Individual layers, for example, can be produced with different fiber orientations. So as the component is being built in these different layers, each layer can take the form of a different fiber orientation, which in turn affects the mechanical behavior of the FRP composite systems. So in here, in this particular project, we've looked at individual layers being selectively reinforced with different fiber orientations, and that resulting in a load sharing with low variation between the share. So what that means is it's a very, very low variation of different layers experiencing different kinds of load sharing capabilities, and not all failing once together, but failing sequentially and having a progressive damage behavior. So if we see this particular aspect here, this is a pultruded GFRP that we've seen before, brittle failure, very, very linear elastic to failure, less than 1.5% strain, and also seen to be very, very, very strong and very high in elastic modulus. When we look at steel, which is the other end of the picture, we have a very nice ductile pattern. This is grade B steel with that 400 MPa and the 250 MPa yield strength. But that necking happens and there is ductility, a yield plateau, and at least 2% strain at failure. So compared to this traditional GFRP, we've seen that using the 3D printing with different orientations, here I'm showing a sequence with 12 degrees fiber, 24 degrees fiber, and 30 degrees fiber, all stacked up to form one fiber system, one FRP system. So this new FRP with progressive sequential drops, this particular composite was loaded under tension. And you see that there is a progressive failure. Not all layers fail at once, resulting in this brittle explosive failure, but there is a sequential failure where every layer fails one after the other in a progressive sequential pattern. This in turn resulted in a progressive pattern of failure with resulting in a more ductile, pseudo-ductile behavior that can have and see much more improvements in the future in order to improve this and get a more ductile, non-linear kind of a behavior. So if we see that ductility, very, very high ductility when you compare it to pultruded traditional GFRP, we're still not with the steel and on par with the steel, but we're hoping that the improvements that we see in the future can bring that. So currently we're working with Transpo Industries to bring in polymer concrete. We are working with the polymer concrete that they very generously donated to OU Fierce Lab. And we're looking at how these ductile FRP can be bonded into the polymer concrete beams in order to understand their reinforcement behavior, in order to understand how this progressive failure can affect the resulting beam behavior. The reason we are using polymer concrete currently is because we do not know how 3D printed FRP can have bond with concrete related products. So because polymer concrete is a resin-based concrete system, we are currently exploring and investigating the behavior with the polymer concrete material. Other improvements that we see in the near future with alternative bonds in 3D printed FRP. Bond between layers is a very, very crucial aspect in how the failure happens. So there are different kinds of failure and damage parameters that happen in the overall failure of the composite. So if we consider these as the different layers of FRP, and the yellow color represents the matrix itself, there's fiber pullout, there's fiber bridging, there's fiber matrix debonding, and fiber failure and matrix cracking that happens in FRP. These different kinds of failure mechanisms can be modified if the bond is affected and bond is modified. For example, if there is a dampened bond between these two fiber layers due to a dampened and a weakened interface of matrix modification, there will be different kinds of failures happening at that interface. So in 3D printed FRP, we're looking at improvements in terms of how the spool itself can be modified. I've talked a lot about nanomodification of resin, but those were thermosetting resins. And now we are dealing with a totally, completely different behavior, which is a thermoplastic resin. Nylon, which is one of the major thermoplastic resins used in 3D printing. We are looking into how it can be nanomodified and using filament makers to produce actually spools of 3D printing in order to print different kinds of nanomodified FRP composite systems in an effect that it will influence that bond it has with fibers and that thermoplastic resin. If we consider 3D printing, one major advantage we have is this particular bonding of crystals, because these are all thermoplastic resins, thermoplastic spools that are built one on top of the other in terms of layers. This particular crystallization and bond that is resulting with this is a very, very crucial aspect for the resulting component that we can produce. So if we affect this bond by modifying parameters like temperature and using different kinds of dampening mechanisms, this particular layer-to-layer interface can be affected. After we affect those interfaces, strong and weak interfaces can behave very, very different from each other. Matrix and fiber interface can be strong, but the crack propagates very easily between layers. But let's say if the interface is weak between the matrix and the fiber, we have much more of a interlaminar and along the fiber direction failure that can result in very different mechanical behaviors. I would like to conclude my talk with important acknowledgements. Of course, the Southern Plains Transportation Center for providing this opportunity, the Oklahoma Transportation Department, the ODOT, and ABC-UTC for this wonderful opportunity. Dr. Zaman for giving me this platform to explain and to demonstrate all these different kinds of work that is possible, and that is the hopefully the future that we can look at. Dr. Mahmoud Rada Taha from the University of New Mexico and his team, where I had my PhD studies and did all my dissertation related work. And the funding agencies for my work, which is NMDOT, Sandia National Labs, and of course UNI. I'd like to, of course, thank my current team of the OU team that we are working currently alongside different kinds of students who are in different levels in their studies. Alexandra, who is an undergraduate student and heading to her accelerated master's program. Haiba, who has already started his accelerated master's and is currently working on the polymer concrete project. Esther, who's an undergraduate student, and I have incoming PhD student in the fall, Ali, and our lab manager for helping us with various things. Funding agencies, the Vice President for Research and Partnerships, the Alan Alda Center Women in STEM, and for, of course, transport industries for providing their generous donations. These are some journal papers, patent and conference papers that are available to see if you have any additional things that you want to refer to. And of course, I'm open to any questions and comments. Thank you.
All right, thank you. That was wonderful. And for everyone who's curious, especially for those publications, we'll have a link to this presentation posted on the SPTC website later on. And before we get into questions, I also want to briefly mention that our next webinar is going to be on April 1st from 10:30 to 11:30. It'll be a hybrid seminar. You'll have an in-person option, but also encourage online participation as well. It'll be from Dr. Elham Finney from Arizona State University. So look forward to announcement for that in the coming days. So we have a couple questions already posted in the chat. I'll go ahead and relay those. And then if there's anyone who wants to raise their hand or unmute and ask questions, please feel free to do so. So this question is from Dr. Zaman. He asks, how does FRP compare with other materials cost-wise for repair/rehabilitation of infrastructure? And what are the prime infrastructure repair/rehabilitation candidates for the use of FRP and why?
Thank you, Dr. Zaman. So cost-wise, we're looking at very close competition between FRP and other materials. Cost currently is looked at on a more lifetime aspect, because for other materials, for maintenance and long-term durability, the cost associated is very high. FRP, on the other hand, poses a much more poses as a much more better candidate because of its long-term durability and maintenance aspects. So the replacement cost is at least for 100 years, you can see a more durable infrastructure. As for the candidates, and I would also like to add, I've talked a lot about nanomodified resins, and based on a cost analysis, we've seen that there is a 10% increase of FRP with and without nanomodification. So that also comes into picture when we're looking at long-term maintenance. What are we interested in? Are we interested in current associated costs? For sure, but also in the long term, how these candidates can provide to be much more beneficial. In terms of candidates for strengthening, we're looking at reinforced concrete beams for sure, because that's where we see a lot of corrosion and different kinds of challenges with corroding steel. So that's something I can think of currently.
All right, do we have any other questions? It looks like we have one question from Jason Langhammer. He asks, do you have any recommendations for design/capacity calculation related resources?
So ACI 442R provides very, very important recommendations for both strengthening capabilities and also calculations for this design aspect. However, there are a lot more improvements that researchers are currently working on adding to those existing guidelines. I can definitely share some material with you that are ACI, non-ACI related also, and other papers that are providing guidelines in order to improve on the existing processes.
Right, as we wait, you can post your questions in the chat, or if you want to raise your hand or just unmute yourself, you can ask a question as well. Well, if we don't have too many more questions, are you comfortable with people sending email questions if they have any after the fact, or?
Absolutely. Let me include my email right here.
Okay, perfect. I know sometimes, especially when I attend presentations, I always think of questions like the next day or something. So that'll be helpful. Great.
And So I'm new in Oklahoma. I came here in August of 2021. I am really looking forward to working on any local Oklahoma projects for strengthening. My husband also is in the same industry, and we talk about FRP every day, all day. It's our bread and butter. But he keeps telling me about a certain bridge while driving to work that has entirely exposed steel. And I'd really like to discuss about that particular bridge and see if there is any open way to kind of talk about strengthening that particular bridge or any other bridge that really we can do some strengthening on. So very excited and looking forward to getting FRP more and more into Oklahoma related projects and strengthening applications. Thanks, Jason.
Michael, there was one question regarding Oklahoma application in potential in Oklahoma. I guess it may have been directed to you or Shreya. I do not know. Could you ask the or repeat that question, Michael? I don't know whether you got it or not.
Do you mean the last one from Jason?
Yeah, probably so. Is that the application potential in Oklahoma?
Any local Oklahoma projects for
Local Oklahoma projects, yeah.
have worked on, yes.
Oh, okay, wonderful. Thank you.
All right. Well, if there aren't any more questions, I'd like to have everyone, virtually, give a round of applause. I think Dr. Vumaganti did a great presentation, and we're very fortunate to have her at the University of Oklahoma. So again, Dr. Vumaganti, thank you for your time, and we appreciate everyone attending for this seminar. And as a reminder, we will have another one on April 1st. Stay tuned for information about that. So thank you very much. We appreciate your time.
Thank you so much, Michael. Thank you so much, Dr. Zaman, Dominique, for providing this opportunity. I had a great time, and I look forward to receiving any emails. I'm so open for conversations, discussions, and even driving around and looking at some structures potentially that could benefit from these materials. Thank you.
Thank you.
Thank you, sir.
Bye. Take care.